Okay, good morning everyone. I think for today's class I will just to finish off what we did before. Okay. So this is the homogeneous linear equation with constant coefficient. So this is a higher order differential equation. And we have the first method is the reduction of order. We did that I think last week. And now the second method is if we have homogeneous. What is homogeneous? It is when the differential equation equal to 0. So we call that homogeneous. Okay? So for higher order, especially for the second order, if this is equal to 0, we can rewrite this and perform. So we can let this the order becomes just like m, okay? Because this m is suppose that this is going to be our solution. So we let the solution equal to e to the power of mx, which later we can see that we can perform some quadratic formula. So basically, what we are going to do is we are going to change the order, becomes an expression in quadratic equations. So basically, when we factorize this, or when we are taking the discriminant, we can know what kind of roots that we are going to have. We can have at least 3 categories. Okay, 3 categories. We can have that positive, the discriminant positive, which has 2 different roots, 2 different or distinct roots, and then we have the discriminant that is equal 0, which means that it has this repeated roots, and then we have it should be less than 0. So should be less than 0. It should be less than 0, which means that this is going to be having a complex, a conjugate complex, or it's not a real number. So for case 1, for a positive discriminant, so we can have these 2 distinct roots which are expressed in our solution 1 and solution 2. So the total solution, or the general solution for this homogeneous equation will be 1, and then we have the root 1 and root 2. Okay? And we need to include the constant here, okay, as in the expression. And these 2 functions, it needs to be linearly independent, okay, linearly independent on the whole interval. Okay, this is case 1, distinct real roots. Okay, maybe to make it more clear, let me copy this, and maybe let me cut this and put into the another page here. Okay, maybe here. Okay. Now, case 2, this is when the discriminant is equal to 0. We call this case as repeated real roots, which means that m1 is equal to m2. So suppose that this is the equation, we call this auxiliary equations. So m1, in this case, if m1 is equal m2, then we can find the m through the quadratic expressions negative b over 2a. Okay, this is finding the minima or maxima value, right? And then from here, we can write negative b over a is 2m. And then from the previous one, the second solution, so if you remember from the reduction of order, we can get the second solution, y2 is equal, maybe let me put down here, is equal E with m1x. So this is if the y1, so suppose, let me write it down there. So if y1 is E m1x, okay. And then from this expression, m1 is negative b over 2a. So y2 is integration e to m1 x e to m1 x dx. And then we can cancel that out, m1 x dx. So this will be x e m1 x. Or here we can also write the m or 2m1 is equal negative b over a. To get the value of 2m1 on the expression on the integrations, okay. Then the general solution. So the general solution, we are combining the y1 and y2. So y is c1 e m1x plus c2x e m1x, since m1 and m2 are the same. Okay. So we need to have a second expression that is linearly independent. So this is the general solutions. Okay. So the other case, so case 3. This is when we have a conjugate complex roots. So here is when the b squared minus 4ac is less 0, which m1 and m2, they are going to be complex. M1 will be, let me write alpha plus I beta, and M2 will be alpha minus I beta. The alpha and beta should be a positive number, and this should be a real number, and the I is for the imaginary, so I squared is negative 1. So we can write y is c1e, and then write all the alpha plus I beta x, just change m1 to the alpha and beta, and then plus C2E alpha minus I beta x. But since we have the complex, the imaginary number, we would like to have the real functions instead of the complex exponentials. So let me write here in practice. Need to use real functions. Okay. So to get the real functions, we are going to use the Euler formula. Okay. So Euler's formula, which E with power of I theta equal cosine theta plus I sine theta, where theta is any real number. It's actually derived, so let me just write some additional information here. Derived from the Maclaurin series. The e to the x and then sub x with I theta. And then rearrange the structure and we get the Euler formula. But this is just addition, okay? So I think let me copy and take the new page for the whole thing here, or let me write from this one, from the second one. So copy, and then let me put in the new page. Okay? So let me write a new page here and this one. Okay. Okay, it follows from the Euler formula. So, okay, it follows from Euler that we can write E and exchange theta for beta x. This will be equal to cosine beta x plus I sine beta x. And then for the negative I beta x, we can write this is cosine beta x minus I sine beta x. And then as a note, we have cosine negative beta x, which is positive, right, in the fourth quadrant, and for sine it will be negative. Okay, this is for that one, or maybe. So then we can express the E with I beta x plus E with negative I beta x. This will be So if we plus these two, subtract. So we add these two. So this will cancel. So we have 2 cosine beta x, right? So 2 cosine beta x. And if we subtract, this will be 2I sine beta x. Okay, remember that the solution that we have, the solution is C1e. Let me write again. This is supposed to be having an alpha plus I beta and x plus C2e alpha minus I beta x. Okay. So this is solution of any choice of constant. Okay. So this is, let me write first. So this is solution for any constant C1 and C2. So if, okay, so if, right here, so if C1 equals C2 equal 1 and C1 equals C2 equal -1, we are going to have 2 solutions. So y1 will be E alpha plus I beta x plus E alpha minus E beta x. Okay, this is for 1, and then for this second one, this will be E this will be minus sorry, this is wrong. It's supposed to be C1 is 1 and C2 is -1. But we can write the y1 and we can factorize the E with power of alpha x, right? So we can write this is E beta x plus E negative I beta x, in which we have done and simplified this into 2 cosine. So we can exchange it with 2 cosine. Okay. So we have, this will be 2E and then cosine beta x. Or let me describe this. This is 2 cosine beta x. Okay, let me write there. Okay. The y2 we can also factorize. So this will be 2IE alpha x sine beta x. So this is 2I sine beta x. Okay. So general solution. We are going to write using this and this. Okay. So first is y. It's C1e alpha x. So expression for the cosine beta. And the second is expression for sine. Or we can factorize the e and then write C1 cosine beta x plus C2 sine beta x. Okay. And what is alpha and beta? Again, that is our conjugate complex. Okay, so let me write here that M1 is having alpha plus I beta. M2 is alpha minus I beta. And how we get the conjugate complex? From the solving the quadratic equations. From the quadratic equations, we might get the complex. And as long as you can describe the complex, the one that has imaginary number, it goes to the beta side here. And the one that has the alpha, this goes to the real number here. Okay. So basically, as long as you can get the M1 and M2, or getting the conjugate, you can just put into our expression here. Okay. And this will be the solution. Perhaps I will give you maybe later additional videos on the Euler formula. Why it's one of the, I think, the most important mathematical equations. I think because it's actually making the imaginary number applicable, or we can treat the imaginary number as in the real number. Okay, let me give you some examples after this. Example that represent the case 1, case 2, and case 3. So case 1, again, it's when the discriminant is positive. So M1 and M2 are distinct. Case 2, when M1 is equal to M2, we have repeated roots. And case 3, when the discriminant is less 0, which means we are going to have a complex, conjugate complex. Okay, let's go to some example. So example, solve DE. So first is 2y double prime y prime minus 3y equals 0. So again, every time you see differential equation and you see that it's not the first order, it's second order, it's equal to 0, we are going to say, okay, it's homogeneous. So we can exchange this y, all y, with some expression m, or any variables you want. And we say that this is the auxiliary equations. So auxiliary equation. So we can change all this, become 2m squared minus 5m minus 3 equals 0. Okay? And then we can just factorize or find the m. Okay? And I hope you are familiar with that, right? One method that usually I'm using, if for example in the quadratic equation, usually I draw a table like this. And then choose which variable that can be, when we are multiplying, it's going to be the same with the original one. So maybe 2m and m is 2m squared, right, if we multiply. and then the right one. To get negative 3, there are several possibilities, either negative 1, 3 or negative 3, 1. So I think because the middle one is negative, so I think this will be the best way, right? Because this is, if we cross multiply, this will be negative 5 if we add both of them. So we get the factors, that is 2m plus 1 and m minus 3. So m1 is negative 1 over 2, m2 is 3. And I think if you mix 1 and 2, it doesn't matter, it's the same thing. Okay. So y is c1 e negative half x plus c2e 3x, and that's it, the general solutions. Second example, y double prime minus 10y prime plus 25y. That this be equal 0. Okay. So again, this is homogeneous, and we can directly write the auxiliary expression. So we can just exchange to m squared plus 25 equals 0. So this will be, we can factorize directly, right? M minus 5 squared. So we have M1 equal M2 equal 5. So this is, so the first one, we say this is the distinct real roots. The second one is the repeated real root, because they are the same. And based on what we have before, we write the first one just same, but the second one, the second m, we need to write c2 multiple with x and then e and then 5x. So this is the solutions. And the third example, let's say we have this. So again, we can directly write the auxiliary expression. Okay. And then we solve the quadratic formula. We can use directly the quadratic formula, or sometimes you can use the, let me write here, like that, and we can just complete the square. Okay, so we plus 4, right? And this one becomes m plus 2 squared, and this will be negative 3. So m plus 2 is square root plus minus negative 3. So m1 is negative 2 plus square root of 3i, okay, and then m2 will be negative 2 minus square root of 3i. Okay. Remember, I is so I squared is negative 1. So from this expression, we get that alpha should be negative 2 and beta is square root of 3. Based on the general solution we made before in conclusion, so the solution will be y, e with the alpha x, right? And then we have c1 cosine square root of 3x plus c2 sine square root of 3x, and that's it. So this is for the conjugate complex roots. At least for the second order, we can solve based on the three cases. Distinct roots, repeated roots, and the conjugate complex. But how about if we increase the order, maybe third order or fourth order? So that means every time we can find the m, or the in polynomials, if you remember in polynomials, if we can find the roots or we say the zeros, then we can just adding all this expression into one general solution. Okay. Which means, for example, you have polynomial by degree of 3. Okay, so the solution will be, there will be 3 solutions. Right? It can be all different, or maybe m1 equal m2, but m3 is different. So for m1 and m2, you can express through the second one, and the other one you can express just as usual. Okay? So let me give you the example. So for the higher order equation, so to solve we have this, let's say n order, so plus a n minus 1 plus and then y double prime plus a1 and a0y. We need to solve a n and then exchange with m plus a n minus 1 m n minus 1 plus plus a2 m squared plus a1 m and then plus a0 equals 0. Okay. So if all roots are real and distinct, then the general solution it can be y so basically we write everything up until the last root. Let's say m n x. Okay. So if you have like polynomial degree 4, which means we have 4, okay, four components. And then if the m1 is root multiplicity multiplicity k of n degree, auxiliary equation. Linearly independent solutions will be E m1x and then E or x, this is the repeated one, x E m1x and then x squared E m1x and then x k minus 1 E m1x. So what does it mean? So if you remember, if you have repeated units like m1 equal m2, this m1, the first solution is this. The second one is if it is repeated, if m1 equal m2. So the m2 become, we multiply with x. How about if with three roots, the same repeated roots. Then we multiply again with x. And multiply again with x. So maybe if we have a 4, then we have the first one is this, second one is this, the third one is this, and then the fourth one will be x cubed. Okay. So the solution, so general solution, we can express using all this. So C1E m1x plus C2E or xe m1x plus C3 x squared E m1x plus and then C k x k minus 1 E m1x. Okay. We'll give you some example and then we are done for today. And then some review on how to, if you maybe remember how to solve finding the roots in polynomials, finding zeros for cubic, for 4th order, 5th order. Okay. So let me give you example. Okay, so solve, let's say y third prime plus 3y double prime. Okay, so again, it needs to be homogeneous. It needs to be homogeneous, so equal 0. And this auxiliary equation will still appear after we get through so many methods. This will still appear. Because if you imagine the 0 is maybe another terms, it will be non-homogeneous. But to solve non-homogeneous, we need to find the homogeneous solution first. And then we add the complementary and particular solutions. So we still need this method for most of the methods. So we still need this. Okay, to solve this, we can exchange to the auxiliary. So we can express in terms of m cubed plus 3 m squared minus 4, right? So sometimes we can factorize, sometimes we need to think with some other method. My suggestions is to find the rational zeros or rational roots from this 4 expression, the last term and the first term. Okay. So this is 4, this is 1. Okay. So the possible, we say the possible zeros will be factor of 4 divided by factor of 1. This is actually from the polynomial solution. So factor of 4 means that which number that when we multiply, it will be 4. So we can get plus minus 1 and plus minus 4. So plus minus 2, plus minus 4, right? And for 1, I think it's just plus minus 1. So from all these expressions, so it can be 1, it can be 2, it can be 4. So this number will be the roots. If you have a constant here, then we can take this maybe 2, 3, 4. Okay, if we have constant in the first terms. So the possible zeros, that's the first one. The second one that I would like to suggest, okay. So from here you can trial and error. So put back to the polynomials and find whether it's 0 or not. Okay. Another way is to use what we call the card rule. So how to use this? Basically, let me write as the P of M. Okay. And then we say that for the positive M, we see that there is one change. Okay? So one change, which means that perhaps the possibility is there will be one positive zeros. Zeros is roots. And then check with the negative M. This will be changing to negative m cubed plus 3m squared, and then still minus 4. We have 1, 2. So we have 1, 2. So perhaps we have 2 negative zeros or 0 negative zeros. Okay, how does it happen? I cannot explain further because it's too much, but this is how we do it. So every time we have maybe 3, 5, we need to have. So for example, if we have 3 sign chain, if we have 3, which means we have 3 possibility of negative zeros and 1 negative zeros. If we have 2, we have 2 negative zeros and then 0 negative zeros. We need to minus 2, minus 2, minus 2. Okay? But if we have just 1, then it's only 1. Okay? So which means that we can have 2 negative zeros. So the zeros can be negative, but they can be 2 or 0. Okay? But it must be 1 positive zero. So the way we pick our number, we check the positive one first because it should be at least 1, right? At least 1. So if we choose from this, we have plus minus, right? We have plus minus, but which one we need to prioritize? We can check the positive one first. Okay? So let's try to do that. And how to take the expression, my idea is to use the synthetic division. So we are going to write 1, 3, 0, negative 4. This is from the polynomials functions, okay? And then we try the number. Okay, we can try 1, 2, and 4. Let's try 1 first, okay? 1, so this will be 1, and then 4. I think this will be the answer. So it's 0, so which means that this one is positive zeros. Okay. So we can write Pm is m minus 1. We can factorize and write m squared plus 4m plus 4. And luckily we can factorize further, so we can factorize become m plus 2 squared. So m1 is 1 and m2 equal m3 is negative 2, which means we can write y c1e to the x, okay, and then plus C2e negative 2x. But since the M3 is equal to M2, we write C3x e negative 2x, okay? And that's the whole expression. This is options, okay? You can skip this Descartes rule, and then you can just try one, okay? One by one, it's okay. This is just some thoughts, okay? Some process. Okay? If you want to use this also can be used. At least to check. Okay, that's it. I think we can have more examples later. Okay.